do that, I'll quickly go through what the AZ late-stage portfolio looks like, outline the challenges, and then I'll get on to how we're addressing them. Obviously, I'd like to finish by how we've solved them, but as we haven't done that, you'll have to get a summary of where we've got up to. What I'm not going to do is go through the analytical challenges for oligonucleotides. That's both in terms of developing suitable methods for routine use in the QC environment, but also the methods you require to investigate these. That would take way more time than I have, but the analytical challenge is easily as large as the process challenge in the case of oligonucleotides. So just quickly, our portfolio. I suppose the important point in order to move on is that our late-stage portfolio are antisense oligonucleotides, which means they're single-stranded. And we have them made up of standard DNA, deoxyribose nucleotides, and C-ets. I'll come back in a moment to what the structure of those C-ets are. And some of these are conjugated. I won't really talk about how we make the targeting agent. Sufficient to say that it's this kind of long chain, we generally refer to as GalNAc. We have 3 N-acetylamine sugars at the end, and it adds a fair chunk onto the size of the molecule. If we just look at what our kind of standard structure is, sorry that hasn't come out so well. It's these are described as 3-10-3 gapmers. Which means we have 3 of the C-et nucleotides, we have 10 of the standard deoxynucleotides, and at the other end we have another 3 C-et nucleotides. And we have 6 standard bases, which are kind of distributed along the chain. It's probably worth noting that the backbone here, they're all phosphorothioates rather than phosphates. Of course, that also means the phosphorus is chiral, but let's not talk about that bit. And the molecular weights are, they're large for us. It's more than 5,500. And of course, once you start putting a targeting agent on, that goes up quite a lot. Again, the standard technology for putting these together, and that's the starting point for us. So just to get back to the C-ets. So the C-ets on the left-hand side there, C-et stands for constrained ethyl. So it's a ribose, but it's got another bridge across. So there's 2 carbons added on there. And the standard way of putting them on is that you have phosphoramidite on the that's the 3 position, and then the other end, the 5' is protected with a dimethoxytrital. And in order to go through that standard kind of assembly, we need both of those with all 6 protected bases on there. Obviously, the DNA phosphoramidites are readily available, but all the C-et phosphoramidites, we have to make. So the standard way they're put together is this synthetic cycle. It's solid phase. It's got a lot of similarity to the solid phase peptide synthesis, and it's been the way of making oligonucleotides for, I suppose, for decades now. The solid phase is that blob, and it starts by you add an activator, you add the phosphoramidite, so you add that the nucleotide on, you oxidize or sulfurize the phosphorus up to the what will be either the phosphate or the phosphorothioate. You cap off the any unreacted hydroxyl, and then you detritylate to go around the cycle again. Of course, there are 3 reactions here in construction and 1 in terms of reducing impurity growth. And an important thing here is that you don't remove any of the impurities. as you go through. That oligo stays on the solid phase until you get to the point of taking it off the solid phase, and then you have to go through any impurity removal. So with a 16mer, you have to go around that cycle 16 times. There's 3 reactions. So in terms of yield, you have to face up to the fact that if it's a 16mer and you've got a 99% yield on every one of those reactions, you only end up with a 60% yield when you take it off the column. And what's even more important is that you've got 40% of other oligos in there, because all those impurities are oligos which then come off with you. And the kind of starting point here is actually 2 lots of chromatography. After you've taken it off the column, you have to do the global deprotection, and then there's 2 lots of chromatography. There's no incentive to speed up the chemistry here. The processing time is in that purification. The actual assembly is over really, really quickly. And we're doing better than 99% for each of those reactions now. We're probably getting up into 99.5. But you really start seeing a benefit here if we can get up to 99.7% for each of those reactions, because then we'd really be able to start cutting back on chromatography. So if we look at the kind of overall supply for oligos, this is kind of the picture you get. Falls into 3 phases for the drug substance. The drug product is the bit on the bottom there. So in the small molecule piece, that is really quite like most of our small molecule synthesis. Although, because we're making several phosphoramidites, we're actually going through a lot more stages. If you think about, standard small molecules, we're generally doing, 8, 10, maybe 12 reactions from commercial materials. There's actually more stages in there. The red squares, by the way, are all points for their analysis, analytical in terms of control and release. Then we have the whole section around the assembly, and then the purify and the substance into products. So that's where we do the chromatography. There's precipitations, pH adjustments, getting it to the right. So it's the sodium salt all the way along, and then the lyophilization, and then we hand it over to product. We actually first put this slide together to talk to some pharmacists. So we really had to big up what they do in drug product there. It's, if we'd done it on the same level of detail, it would be a little bit shorter. So as a challenge, if you look at that, and we've got to make tons of these. The peak year volume for some of the oligos that we've got coming through is expected to be around about 2, 3, 4 tons. So first point is that this has got to be expensive, and you're right. But another way of looking at it is, what's the environmental impact of what we're doing here? And at AstraZeneca, we have a target of net zero for the company by 2030, and the kind of waste that we produced in API production is a significant part of our impact and something we have to work on. So just to have a look at a kind of comparison. This is a way of looking at waste for manufacture. PMI stands for process mass intensity, and it's simply the kilos of waste per kilo of product. Kilo of the materials that you use per kilo of product. And that line represents a kind of target that we have for our small molecules. And really, if it's low volume, we allow ourselves a target of up to about 500. That's if we're making kilos. And a target of around about 150 for when we get up into kind of ton scale. If our product is going to be a ton level product. And those red dots represent, where our late stage development compounds are at the moment. So where does oligos come on here? Well, first off, you have to make a, oh, no, wrong way. You have to make a lot more room. And then if you put that on, actually a 60-mer oligo, and that's a naked one, that's without the targeting on it, is actually works out at the starting points for us of about 5,000. So if we make a ton of product, we're going to make 5,000 tons of waste. And if you're interested, because you're thinking about peptides, also that kind of solid phase synthesis, well, they're in a similar place or even worse. I think you've got to say that peptide solid phase synthesis is, I think, probably ripe for a reinvestigation. And it's also interesting is that probably 2,000 of that, 1 to 2,000, is acetonitrile. And for, I suppose if there are any other process chemists in the room who are around 2008, 2010, can remember the kind of great acetonitrile shortage, the acetonitrile drought, that's not a particularly attractive place. Global capacity for acetonitrile is around about 85,000 tons. And as no one actively makes acetonitrile, it's a waste product really, there's not a huge amount of elasticity in that. And we're not the only people who are going to be making oligos. There are plenty of other companies coming along. So that's a serious question for us. But if we're going to start looking at it, let's look at where that material use is. So by material type at the end there, if you look at what's going on here in the synthesis and the purification, large part of our waste, just, where is it? Almost half of the waste is in the purification. If we add in the isolation, that's over half. So I suppose that stresses again the importance that if we can just make those small marginal gains on the individual reactions in the assembly, being cut out, at least one of that chromatography can make an inroad to that waste. And in terms of the isolation, we've already been actually more or less kind of got rid of that because we've got an aqueous solution. Product is an aqueous solution, so we've actually started looking at making solution API, so rather than lyophilizing it, which is also quite a high energy process. We've got a solution API, and we've had, like plenty of other companies, we've had very successful discussions with the regulators about providing the solution rather than the lyophile. And on the synthesis side here, it's actually quite surprising how much of that is taken off with detritylation. What doesn't come out is what's the impact of the C-et phosphoramidite synthesis. But if you look at the life cycle analysis, and so you look at equivalents of CO2, you can look, so you kind of break it all down in a slightly different way. There's obviously a lot there about the others. But the API materials, you can see actually that the C-et amidites, they're quite a chunk of our CO2 equivalent. What's interesting is, although that GalNAc piece is really quite large, if we do make one with a GalNAc on, its contribution to the kind of CO2 equivalence is actually quite small. So that if you were to make a targeted molecule, it only adds up a little bit more, but those targets usually reduce the dose by at least a factor of 10, so it's worth doing from an environmental standpoint. So as the building blocks do contribute a large amount, they kind of fit in here, and actually the main part of the synthesis, I'll just talk about how we go about, or how we start to look at the synthesis of the C-et amidites. So when we started, it still says ISIS on there, they're now Ionis. The route we inherited was started from diacetone glucose. There were several other published routes to kind of C-et amidites, one by Hanessian there. But there was one of the features of them is that they all add the the methyl of that, for that kind of constrained ethyl, the constrained ethyl piece, by a methyl addition to an aldehyde. And that gave us, alongside, there was some stereochemistry, but that actually washed out. We also get a significant amount of this constrained methyl, so kind of a des-methyl impurity. Now, if this was the API and we were getting 0.2, 0.3% of it, 0.4, I wouldn't necessarily be over worried. We'd qualify it, we'd do what we can to stop it, but we can live with that. We have material that's around 0.5, but because of the way we make it, the way we assemble the oligo, and the quality we're getting off, that 0.5%, there's 6 of them. It becomes 3% of an impurity. So, and we're not going to separate it on chromatography. We've got enough other impurity problems. We've got to make sure we don't bring something through from the starting material. There were some other published ones I won't bother about. So we needed a synthesis that avoided that step. You can also look that in the so we started from the diacetone glucose. Obviously, I wish I'd paid more attention to those carbohydrate lectures when I was here. But what we found eventually, for control of the stereochemistry, and also the addition of that C5 hydroxyl without having to do any other messing around with the we just managed to translate through all of the carbons from the diacetone glucose through to the CEAT, this aldol, which is with formaldehyde. A whole load of conditions to control the stereochemistry, but also we got complete addition in there. We can now have an intermediate with the right carbon backbone. We could translate that through. And so this is the complete route to the CEAT nucleosides, which I won't go through any detail. But we also played around with the protecting group. So we had this key intermediate, the dibenzyl mesylate, which now offers a nice crystalline intermediate. We can clean it up, and we can take it through to all the phosphoramidites. Let's quickly slip that through. Obviously, in terms of processing opportunities for the oligos themselves, for the assembly, and we're doing this with other companies. There's actually quite a lot of pretty competitive work here. This is an issue not just for AZ. This is an issue across the industry if we're going to have oligo drugs. So we're looking at other ways of, other supports than solid supports. So you tag the solution, you've got something there which may be easier to control than the beads that we have. You may not have to do it in a solid phase. They can help actually solubilize it. Blockmers, that's a kind of a standard approach in the peptide world. Non-templated biocatalysis, that would also allow us to get it to do much more of it in water. More effective synthesis, that's obviously what I was talking about in terms of getting every single one of those yields up. And obviously in terms of improving the chromatography. Flip that over. Just some summary thoughts. So that's a single product making tons consumes more than 1% of the global acetonitrile capacity. I haven't really got on to what are the critical quality attributes of the resin. And indeed, actually, how do we investigate the resin to determine what they are? Obviously, there's talk about the CEAT phosphoramidites. But actually, there's more work going on to I suppose in medchem, to produce other variations of those nucleotides, and I think I can be fairly sure they're not going to be simpler. There's environmental impact all the way across the supply chain. However, in terms of why I think we're going to get somewhere, there's plenty of processing technologies to be considered. Targeting agents do actually have an environmental benefit, and there's lots of cost savings to go at here. And with the targets for the company, actually in terms of oligonucleotides, getting funding to look at new technology, we've been reasonably successful in terms of doing that because of the big environmental and cost challenges to go at. Also, of course, Ian won't be surprised to know that I actually haven't done anything at all. It's all been done by other people. So I ought to acknowledge all of those people who've done the work, and of course those not on the slide, to acknowledge Ian's help at the start and actually all the way through my career. And thank you all for your attention.